Okay, so this is an example of quasi convex functions here. It says that for these functions, when we pick up randomly 2 points in the domain, and we first do the linear combinations of these 2 points, we get lambda x plus 1 minus lambda anti y here. Okay, and we look at the image of that linear combinations, and we found that it always smaller or at least equals the max of the original 2 point. I mean the image of the original 2 point here. And in this specific case, when I draw it this way, it's smaller than the f of x, right? And you can play around it and to see like, okay, is it really true that no matter how I set up these 2 points, it always satisfied this property? Okay, you can play around it. And one more thing to add is that if a function is convex, then it implies f is quasi-convex. But it is not true the other way around. Okay? As you can see here, like if you do the same thing on your right-hand side, you will figure out that, okay, so this doesn't fit that property, but that one fit this property. Okay, so for the proof, it's not that hard, so you can try it by yourself. Okay, and of course we have convex, then we have quasi-concave as well. And the way we define it is it should be larger or at least equals the minimum of the image of the original 2 point you pick up. Okay, so I'm going to draw another graph here. Okay, so this is an example of quasi-concave functions. Okay, and in this case, no matter how we pick up our candidate or like the point of interest, the linear combinations between 2 points you pick up and you throw it into the functions you have right now, and you will figure out that it is always larger or at least equals the minimum of the image of the original 2 points you pick up. Okay, and in this specific case is the f of x. Of course, you can play around it, and again, if it is concave, then it implied is quasi-concave. And of course, the other way is not guaranteed. Okay, cool. I think I'm going to finish up these lectures really quick, and I will let you go after that. Oh, would that be okay? Yeah, cool. So we have 2 more topics to cover today. So the first one is the separating hyperplane, and I also make a mistake here. I think I should prove that in a more general sense, it's like if we have 2 non-empty disjoint convex sets, that plane always exists. So I'm going to finish up that proof, and maybe we can go through the proof next time. But for now, I'm going to tell you what is the separated hyperplane is. And that's it. Okay, so the definition of it is that, okay, now we have two sets. They are non-empty, disjoint, and convex. And a separated hyperplane is that, as it shows, like you're going to separate these 2 sets with the plane you construct. Okay, so that is it. So we already showed that the plane, how to construct a hyperplane, which is the inner product of a fixed non-zero vectors there, and with all the points on the space, and that will equals to a certain number b there. And that plane, how do you know that plane separates these 2 sets? It has to satisfy this. So when you put all the I should change the notation again, but when you put all the point in set 8 and put it into these equations, like put it on your left hand side here, you will figure out that the number you get is actually smaller than b. And if you put y into your in the left hand side here, you will figure out that the number you get is always larger than this certain numbers b here. Okay, so that's how we can see the plane is separate to 2 set. Okay, so it should be intuitive to see, because when it exactly equals b, then that means that point fails on that point, right? So whenever it is not equals b, then it must be fails outside that plane. Okay, and because we want to separate 2 sets, that means 1 set has to be in one side, and the other set has to be the other side. So one set will be totally larger than the b, and the other set will be totally smaller than b. So that is the idea. And not intuitively, but the way I think, I try to think about this concept is, So it's like we have the candidate, how to say that, potential normal vectors that is going to create a hyperplane that are going to separate these two sets A and B. And for now, if we set B1 like incorrectly, then we may find that okay, so some point in the B will exactly falls on the plane, and then you start to shift the B here. So I change from B1, for example, to B3, and I figure out like, okay, so now the side on the set 8 becomes a problem, and